We were talking about the rate of a chemical reaction on Monday, and now we're going to look at what's called a rate law. It's an equation, and this shows the relationship between the reaction rate and the concentration. So we saw that the rate slowed down as the reaction went on, and that's because the concentration of the reactants are dropping. So here we're going to look at just a very simple reaction where compound A maybe decomposes or something and forms some products, but we only have one reactant. The rate law is the rate is equal to a constant times the concentration of the reactant raised to a power of n. So this K is called the rate constant, and N is called the reaction order. So we'll be talking about zero order, first order, and second order reactions. There are other orders possible, third, fourth. You can even have fractional orders, like a 3/2 order, which kind of seems strange, but there's some strange stuff out there. So for a zero order reaction, N is equal to 0. Well, what happens when N is equal to 0? If that's 0, then that becomes 1, right? And the rate is just equal to the rate constant. So in a zero order reaction, the rate does not depend on the concentration of the reactants, it just stays the same. In a first order reaction, the exponent there is 1. And so then the rate is directly proportional to the concentration of A. In the second order, that exponent is 2, and now the rate is proportional to the square of the concentration. Questions? So I told you there'd be graphs. There's some more graphs. So this is looking at reactant concentration versus time. So here's the concentration of that reactant, and here is time going on. And we have the 3 different orders graphed. And so for a zero order reaction, we see a straight line here. The concentration of A has a linear dependence on time. For first and second order, the concentration is still decreasing, but it slows down as the reaction goes on because the rate is changing. Just looking at a graph like this, you can't determine whether it's second order or first order, but you can identify a zero order reaction this way because it's linear. We can also look at rate versus the reactant concentration. So how does the rate in molarity per second change as the concentration of the reactant is changing? Well, if the reaction order is 0, the rate does not depend on the reactant concentration, and so it doesn't change. It's just constant, same all the time. In a first order reaction, the rate will be directly proportional to the concentration, so we have a linear relationship. And then second order, it's proportional to the squared, and so we have an exponential relationship. The higher the concentration, the higher the rate. Any questions? Yeah.
What units are like the rate constant and concentration?
Concentration is almost always going to be molarity, moles per liter. And what we're going to see is the rate constant units are going to be different depending on what the rate order is. The reaction order. Yeah, good question. Anybody else? Okay, so let's talk about these in order. A zero order reaction. The rate is independent of the reactant concentration, so the rate is just equal to a constant. Now, how does this happen? Because it seems to make sense that as the reactant concentration gets smaller and smaller, that you have less slower reaction. So how can it just stay the same? Well, this is going to happen in certain situations. A sublimation is an example. So here we have a solid substance and it's subliming, which is going directly into the gas state. It's not melting first. So we're looking at the rate at which this is subliming and going into the gas state, and then we see that it's gone into the gas state because it's depositing on this glass tube up here with ice in it. Well, what happens here? When the first layer sublimes, what's underneath? Another layer. Is it about the same size? Yeah, it's the same size. So as the reactant disappears, the amount of reactant available to react is still the same. So it doesn't depend on the concentration. So the amount of reactant available for reaction is unaffected by changes in the overall amount of reactant. As the reaction occurs and goes on, this piece of whatever it is going to get smaller and smaller and smaller. But we still have the same amount of stuff available to react. Does that make sense? Zero order is kind of weird. But the math gets really simple, so that's kind of nice. So first order reaction, the rate's directly proportional to the concentration of the reactant. So as time goes on, the rate will slow down because the reactant concentration is decreasing. Second order is proportional to the square. And so here the rate is even more sensitive to the concentration because it's related to the square of the concentration. Okay, so let's see how we're understanding things. So talking about the same kind of reaction here where we have just A going to products. A doubling of the concentration of A causes the reaction rate to double. What's the order of the reaction? 1. Yeah, it's going to be first order. Because the rate is equal to a constant times the concentration of A. Raised to the 1 power, we just don't write that 1. So if the concentration is twice as large, then the rate will be twice as large. Sometimes when we see the word doubling, we think second order, but no, is first order. Any questions? If it was zero order and we doubled the concentration of A, what would happen to the rate? It would stay the same because it doesn't depend on the concentration. How about a second order? Double the concentration and then the rate will what? Quadruple because it's that squared, right? So how do we determine the reaction order? This is important. The order of a reaction can be determined only by experiment. You can't look at the chemical equation and say, oh, this is what it is. You can only do it by experiment. Okay, so we can determine this by experiment. And one way to do this is called the method of initial rates. And we're going to do an experiment, not next week, but the following week, where we're going to use this method, the method of initial rates. So what you do is you measure the initial rate of the reaction, and you run the reaction with several different concentrations of reactant. So here, when the concentration of reactant was 0.1, the initial rate was 0.015. We double the reaction concentration to 0.2, and we measure the initial rate. We double it again, and we can see the change in the initial rate. So we can look at what's happening here and figure out what the reaction order is. So going from here to here is times 2. And how is the rate changing? It's also times 2. When we double it again, what happens to the rate? also times 2. So what's the reaction order? First order. Yeah, so this is first order. So then we can write the rate law. The rate law is going to be the rate is equal to a constant times the concentration of A to the first power. With this data here, we can calculate the rate constant because we have the concentration of A and we have the initial rate. So we can find out what K is. If you can use any of these three and you'll end up with the same rate constant. So we could rearrange the equation and say that K is equal to the rate divided by the concentration. If algebra is not your friend, please come and talk to me and I'll get you set up with one of these so you don't ever have to rearrange an equation again. For the rest of you, I'm not going to go step by step how I rearrange things. I'm just going to kind of do it. Okay, so the rate constant equals the rate over the concentration of A. So let's just pick the first row there. The initial rate is 0.15, and the units of rate are always molarity per second. And we'll divide by the initial concentration, which is 0.10 molar. And so we end up with 1.5. And what about those units? Well, molarity cancels, and we end up with 1 over second, or per second. So that could be written that way, or 1.5 s to the minus 1, or 1.5 over seconds. And I'm thinking my 5 there looks an awful lot like an s. There. Any questions? Yeah.
I think you forgot a 0 in front of the 15.
I did. Thank you. Yep, so that changes the answers. See those zeros. Thank you very much. So let's fix all of these then. It's 0.15. You saved me so much embarrassment on YouTube. There. Question?
Could we write unit as hertz then?
Could you write it as hertz? That's a great question. You could. We would understand what you mean, but we don't do it. So, not exactly sure why, but usually with the rate constant, we're going to be using time, and the seconds will be needed as units. And so it's clearer if it's s to the minus 1 or something. Yeah, that's a great question. It is the same as hertz. So it is important to, have in your mind that when something is raised to a negative power, that means that it's 1 over that, okay? So s to the minus 1 is 1 over s to the 1. And you'll see it both ways. Any other questions? Okay, so here are 2 other examples. This one is 0 order. They're just telling it to us off the top. So here, again, they're doubling the concentration of A, going from here to here, times 2, from here to here, times 2. And what happens to the rate? It stays the same, right? It doesn't change. So that would be times 1, and this would be times 1. The rate isn't changing when the concentration does. Well, that's the zero order, right? The rate is equal to just a rate constant. Doesn't matter what the concentration is. Second order, doubling the concentration. what happens to the rate? Like, I can't do that in my head. What's 60 divided by 15?
4.
It's 4. So this is times 4. And then going from 60 to 240 is also times 4. So double the concentration, quadruple the rate. Second order. So the rate there is equal to the rate constant times the concentration to the second power. And that's why when we double this, the rate gets quadrupled. I'm sorry, yes, quadrupled. So sometimes we can look at data like this and we can just see, well, how's this changing and how's that changing, and we can figure it out pretty easily. I would recommend trying that first. But sometimes it's just not very obvious. Like maybe the experiment wasn't set up very nice and these are just kind of random seeming numbers, and you go from here to here and it's 1.78, and then you're like, well, how does that help me out? Doesn't. So we can use this equation here. And let me show you where that comes from. So the rate is equal to the rate constant times the concentration raised to the n power. That is true for any concentration. So what we can do here is we can look at, we can take this and we can divide it essentially by itself. N doesn't change, the reaction order is constant, it's the same. And the K doesn't change, but the concentration can change. And so we're just going to do a ratio. So usually we put the second rate first and divide by the first one. And that's just because usually we start with a small concentration and go to a larger concentration. And so when we do rate 2 over rate 1, we get a number that's larger than 1 instead of a small number. So let's look at how we could use that to determine the second order rate here. Well, this is the second row, so we'll use that as 2. So rate 2 is 0.060 molarity per second, divided by the first rate, 0.015 molarity per second. And that's going to equal the rate constant times the concentration. The initial concentration is 0.10. I'll put the units in there. Molarity raised to the n power, divided by the rate constant. I did that wrong, didn't I? Yeah, I did the first one. I'm supposed to put the second one on top. Ooh, caught that one myself. So then on the bottom, we're putting the first one, also raised to the n power. You may look at that and say, well, how does that help? That doesn't look very helpful. Well, the rate constant doesn't change, and so that cancels out. Here we have a number raised to a power divided by a number raised to the same power. We can simplify that. So we can say, well, that's going to be the same as this fraction raised to the n power. And that's a little exponent voodoo. So let's figure out what these fractions are now. So 0.06 divided by 0.015. And as we already figured out up there, that's 4. So that's 4. 4 equals this number, 0.2 divided by 0.1, which comes out to be 2 raised to the nth power. So what's the exponent? 2, because 4 is equal to 2 squared. Okay? We'll do somewhere we have to do some other things, but we'll just leave it simple for now. Questions? So, per Justin's question, what are the units for rate constants? This is something you can memorize, or it's something that you can understand how to figure out, and then you don't need to memorize it. So how do we figure that out? Well, I'm just going to put the units in instead of numbers. So the unit of rate is molarity per second. So molarity per second is equal to the rate constant. That's the thing the units we're trying to find, right? Times concentration, which is molarity raised to the 0 power, and of course that's 1. So the rate constant equals molarity per second. So those are the units of the rate constant. The rate constant is going to have different units for different order, and it's just whatever units are needed to cancel out the other units. For the first order reaction, again, rate is in molarity per second, and that's equal to the rate constant times molarity. So now we can simplify this. We can get rid of molarity on each side, and we have the rate constant being 1 over second, or s to the minus 1. For second order, again, the rate is molarity per second, equal to the rate constant times concentration squared. Well, let's be a little bit careful here and write this out. So I'm going to divide by molarity squared on both sides. So those cancel out. Now we've got this little mess here. Well, we have molarity on top and molarity times molarity on the bottom. So we can use the top one to cancel one of those that's on the bottom. And so the rate constant then is 1 over molarity times seconds, or molarity to the minus 1, s to the minus 1. Any questions? When we're talking about rate constants and rate orders and stuff, we're not going to be doing a bunch of unit conversions. Time will be measured in seconds. The rate is in molarity per second. The concentration is in molarity. So the rate constant ends up being whatever units are needed so that it comes out equal. Okay, so here's a conceptual question. The reaction A to B has been experimentally determined to be second order. The initial rate is 0.01 molarity per second at an initial concentration of A being 0.100 molar. What's the initial rate when A is equal to 0.5? Conceptual means that we don't really need a calculator to do this, although we might need to do a little bit of math in our heads. So this is the first concentration, and that's the second concentration. How is the concentration changing? It's multiplied by from 0.1 to 0.5? What do we multiply 0.1 by to get 0.5? It's not that early in the morning. It is that easy. Just 5, right? It's just 5. So going from 0.1 to 0.5, we've quintupled the concentration, right? So, oops. A is times 5. So if this is second order, well, let's just start at the beginning. If it's 0 order, changing the concentration will have no effect. If it's first order, changing the concentration by times 5 will cause the rate to increase times 5. So because this is second order, then the rate is going to be times 5 squared. Okay? So 5 squared is 25. So 0.01 times 25. And even if our mental calculator isn't on, this is the only reasonable choice because it's the only one that has 2.5 anywhere in it. Any questions? We really want to understand how this is working now, because if I lose you here, it's not going to go away. We're going to keep up with this building and building. So does anybody have a question? Because I really don't believe that everybody gets it yet. That never happens. Anybody have a question about that? I can just explain it again. I mean, you don't even have to have a concrete question. You can say, well, I don't understand it yet. Anybody? No? Yeah?
Can you explain again why it's D?
Yeah. So the rate went up by times 5. And in a second order reaction, the rate is equal to the rate constant times the concentration to the second power. So if A is going up times 5, then this piece is times 5 to the second power, which is 5 squared, right, which is 25. And so our new rate is the original rate, 0.100, times 25. Does that help? Okay. Anybody else? Okay. So that's talking about one reactant. What if you have more than one reactant? Because a lot of reactions have more than one reactant. Okay, so again, we're going to look at a generic reaction, A of A plus B of B, etc. We've seen this guy before. So the rate will be proportional to the concentration of each reactant raised to a power. So the rate will equal a rate constant times the concentration of the first reactant raised to some power times the concentration of the second reactant raised to some power. And if you had more, it's just the concentration raised to a power. When we talk about the overall order of the reaction, we're just going to add those exponents. So that would be, oops, not what I meant to do. M plus N is the overall order. Now, we're going to say it again. The rate law for any reaction must always be determined by experiment. We've done a lot of things where we could use the coefficients in the equation to figure out what's happening, right? We did that with the rate. The rate was equal 1 over the coefficient times the concentration of a product. You can't do that here. It's so tempting. It would be so nice if you could, but, you know, science doesn't work that way. Okay, give the overall order and the order with respect to each reactant. So here we have a chemical equation, and we're not going to get any of these answers from the balanced chemical equation. This is the rate law. This is what we have to look at. So what's the overall order? 2. Overall equals 1 plus 1, which is 2. We're just adding the exponents. Normally we don't write the ones, but we put them there here just to make the point. So the order with respect to hydrogen is what? 1. That's the exponent on the hydrogen concentration. And with respect to I2, what's the order? 1. So it's first order with respect to hydrogen and first order with respect to iodine, and overall a second order reaction. Let's do another one. Here's a more complicated chemical equation. We got some coefficients in there, but again, we get no information from the equation. We need to look at the rate law. So what's the overall order for this one? 3. We're going to add the exponents. 1 plus 2 is equal to 3. And then we can look at the order with respect to each of the reactants. We've got hydrogen. We're not looking over here. We're looking at the rate law. What's the order with respect to hydrogen? 1. And what's the order with respect to? No! It's 2. You just have to be prepared for that, right? It's all caps. It's yelling. No. Any questions? Okay. Consider this equation. The initial rate of reaction is measured at several different concentrations of the reactants with the following results, shown here in this table. We're not going to read those because that's silly. From the data, determine the rate law and the rate constant. Go. Yeah, what? I'll walk you through this. Okay. What we did with the simple reaction where there was only one reactant is we looked at how does the concentration change and how does the rate change. We have to be a little bit careful here because we have 2 reactants, and so we need to look at one change at a time. We can't compare things where both of them are changing. So this experiment was done well. From the first trial to the second, this concentration doubled and this concentration stayed the same. Yeah? So here the concentration doubled. And again, you can figure out what that number is if your mental calculator's broken. 0.02 divided by 0.01 comes out to 2. And so here, this is just times 1, which means that's not changing at all. We don't have to think about that one. And then what's happening to the rate? And you're like, well, let's get the calculator out. It's okay. 0.0069 divided by 0.0035 is 1.97. Well, so this is more realistic data where we don't always get perfect numbers. 1.97 is really close to what? 2. So this is times approximately 2, which is close enough. Because anytime we make a measurement, there's going to be some error, some uncertainty, right? So things don't always come out perfect. Okay, so if this one doubles and the rate doubles, what's the reaction order for this reactant? 1, because you do something to the concentration and the rate changes exactly the same way. So our rate law is going to be the rate is equal to the rate constant times the concentration of the first reactant. And we just figured out that that's first order. I'm going to write the 1 in there. Times the second reactant concentration raised to some power. We haven't figured that one out yet. So to find the order with respect to chlorine, we need to compare two rates where the CHCl3 concentration didn't change. So the second and the third line are like that. Let's just use a different color here. So 0.02 to 0.02, there's no change. So then let's look at, well, what happened to that? That was doubling. And what's happening to this? Well, again, 0.0098, and that one's not nice whole numbers. So let's just do 0.0098 on the calculator, divided by 0.0069. And this is equal to 1.42. That's not obvious, right? It's not first order because when this doubled, this did not double. It's not 0 because this did change. It's also not second order because it should have quadrupled. What do we do? Well, this is where we have to use that rate equals over rate equals because it's not obvious. So rate 2 over rate 1 is equal to the rate constant times the first concentration. And here we did determine that that was 1, so we can leave that, we can put that in there. And then we've got Cl2 raised to a power that we're trying to figure out. And these are concentrations in the second condition. So the rate is equal to the rate constant times the concentration of this raised to who knows what. We can write the same rate law with subscripts of 1. It looks like, ooh, this is this big equation I have to remember. No, it's one rate law divided by the other rate law. It's a little bit like what we did in Chem 1A where we took PivNert and divided it by PivNert. So everybody see what I'm doing there? This is what we know about the rate law. This is going to be true for all of these experiments. If the rate is equal to this, then we can divide by the same thing and we're not changing anything. We're dividing both sides by the same thing because rate 1 is equal to this. Oh, I made a mistake, didn't I? What did I do? You see it? Here, Cl2, I put a 2 there. Maybe because I just wrote a 2, I don't know. But that's not right. It should be 1. Because we're doing 2 over 1. You can do 1 over 2. You were confused?
I was confused because I was like, is she putting the 2 because the other 2 is on the chart? I was like, okay, I'm just going to go with it.
Yeah, don't just go with it. Always ask me, okay? Because like I said, I'm not a morning person. Other times I've taught this class, it's been from like 6 to 10:30 at night, which I like better, but a lot of students don't. Anyway, so look at what we've written, make sure that we didn't screw it up. Okay, so we're looking at this, it's a big old mess, and we're like, well, how is this going to help us at all? But we can cancel some things out, right? because the rate constant is the same for both of them. So we cancel that out. The concentration of this reactant in the first and second conditions, this is 1 and this is 2, those are the same. It didn't change, so that also cancels out. So we have rate 2 over rate 1 is equal to this concentration to a power divided by the other concentration to the same power. So we're going to take the numbers now and plug them in. So this is what we're calling number 1, and this is what we're calling number 2. Because I know there's 2s and 1s and stuff all over the place. So rate 2 is this one. 0.0, oops, I'm losing zeros today. And just so it looks a little cleaner, we're going to leave the units off. And we're going to divide that by the first rate. This is the second rate divided by the first rate. I'm wishing I left more space, so I'm going to make more space. And then we're going to divide by the chlorine concentration in the second condition, which is 0.02, raised to the n power, divided by the chlorine concentration in the first condition to the n power. Everybody okay? It's easy to get things screwed up when you do that. So, you put it in. It's always a good idea to go back and look at it, check, did I get them in the right places? Well, we can simplify this by just doing the math in these fractions. Right, so this raised to the n power divided by that raised to the n power is the same as just that whole thing to the n power. And that's an exponent thing. And I'd be happy to give you a short lesson on exponents if you need that. Okay, so 0.0098 divided by 0069, I already did that. It was 1.42. I'm just looking at these numbers. They've got 2 sig figs, right? So whenever you're messing around, it's best to keep 2 extra digits. So I'm going to turn my calculator back on and see what that next one is. It's a 0, so it wouldn't have mattered anyway, but there we are. And then we have 0.02 divided by 0.01, so that gives us 2, and this is raised to the n power. Then we have to do logarithms. Okay, we're going to be using logarithms in this class. And I remember them as being just sort of this mysterious thing that happened when you pushed buttons on your calculator. And it wasn't until the first time I was lecturing and teaching chemistry that I really understood what logarithms are. And once you see what they are, it's beautiful. But we can also do this if we just remember some logarithm rules. So what we're going to do is we're going to take the logarithm of both sides. So the log of 1.420 is equal to the log of 2 to the n power. When you take the logarithm of something raised to a power, that is equal to the exponent times the log of that number. If you don't believe me, there's an appendix in the back of the book that goes over all of this. So the log of 1.420 is equal to n times the log of 2. Well, if I divide both sides by the log of 2, I can figure out what n is. So I've got the log of 1.42 divided by the log of 2 Yeah, there's just not enough room on this slide. Let's go. There's Mr. Bigelow getting excited about physics. My calculator's showing me 506. If we throw one more digit in there too. So these exponents are either going to be whole numbers or nice fractions. Things like 1/2 or 3/4 or something. They're not going to be weird decimal numbers. So what fraction is this close to? 1/2. So n is equal to 1/2. Well, we didn't talk about that. Well, we talked about that it could happen. So now we figured out what n is. It was 1/2. So there we did a. Did I leave extra room? Oh, I did. Well, no, I didn't, but that's okay. Instead of trying to cram more into this slide, I'm just going to go use the next slide. So this is our answer. This guy right here is the answer to A, the rate law. Any questions about that?
I have a question.
Yeah.
Why do we divide in lower two?
Why do we divide here?
No, it's down to
Down here? Over here?
the left side. No, lower two divided by.
Okay, so I had this, the log of I took the log of both sides. So I got log of 1.42 is equal to n times the log of 2. And I'm trying to isolate n and get it by itself. So I'm dividing by 2, log of 2 on this side, so those cancel out, and I'm doing the same thing on that side.
Okay, got it.
It's a little harder to see because we've got this guy in the middle. Yeah, great question. Anybody else? Okay, so first order and half order. Let's go to the next slide and do part B. It wants the rate constant. Well, we have to start with the rate law. The rate law is the rate is equal to the rate constant times the first concentration to the first power and the second concentration to the 1/2 power. You can do 0.5 if you want. Well, how do we figure out what the rate constant is? We choose one of these sets of data and we put the numbers in. Because here we have the concentrations for each and the rate. So there's the concentrations. Here's the rate. The only thing we don't know is K, so we can solve for that. In real data, when you do that, if you do that for each of these, the rate constant is not going to be exactly the same. Should that be shocking? No, because our measurements are not perfect, right? So ideally what you would do is you would do this calculation for each of them, take your rate constants and average them together. We don't care that much about how accurate this one is. We're just going to pick one. So I'm just going to pick the top line because that's easier to track. And so here the initial rate, 0.0035 molarity per second is equal to the rate constant times 0.10 molar to the first power times, no, I did it again. 0.10 and 0.100, and this is to the 1/2 power. In Chem 1A, I encouraged you to always rearrange the equation first, then plug the numbers in. Here, there are some times when rearranging the equation first is just a nightmare. And so sometimes you can do it that way, sometimes you just plug the numbers in, and this is where the number solver on this calculator is great because you can type it in just like this and press a couple buttons and it's going to tell you what K is. It's nice. It's really nice. Otherwise, we're kind of rearrange this in our heads maybe. So I'm going to take this number, 0.0035, and I need to divide by this one. And I need to divide by this one to the 1/2 power. And so I get K is equal to 3.5. Left out a unit. What are the units on that? Well, for those of you that I lost by jumping directly from here to here, I'm going to write out what I did in my head. So I divided by 0.01 on both sides. So those cancel out. And I divided by this on both sides. So I did the math there. I got 3.5. How do we do the units? Well, let's simplify the units over here on the left side. So I have a molarity in the numerator, so I can cancel molarity in the denominator. And this unit, molarity to the 1/2. So I've got molarity to the 1/2 down here. And this is in the denominator with the S. So my units are molarity to the -1/2, second to the -1. And the answer up there is wrong. Up here it says that the unit is S to the -1/2. But did S get involved with that 1/2 exponent? No, it didn't. So I've been through these slides several times. We never found that mistake before. Or maybe we found it and I said I was going to correct it and I never did. That's more likely. Okay, who has questions about this? I wouldn't dare do something like this on the second day of Chem 1A. Because people's heads would explode, right? Or they'd melt into a puddle or they'd run screaming into the night. Because that's just way too much math. But you guys made it through Chem 1A. And so this might be a little scary. You're like, ooh, that looks kind of messy. But we can do it. For some of you, you're like, oh yeah, I saw how you did that. Great. I'm not talking to you anymore because you don't need me to talk to you anymore. For those of you that went, what? Again, I'm really pushing this calculator because all you have to do is type in the blue equation, press a button, and it tells you 3.5.
We also have some in the library still.
They have some in the library. We also have a bunch up here. Actually, let's do that. Okay, so let's look at this. So the reaction was experimentally determined to be first order with respect to oxygen, second order with respect to no. The diagrams shown here represent reaction mixtures in which the number of each type of molecule represents its initial concentration. Which mixture has the fastest initial rate? Well, we can't just plug things into an equation, right? We have to think about this one. So in panel A, we have an equal number of NO and oxygen. Right? So I'm just going to make a little note of that because we're going to forget by the time we get to C. So here, they are equal. In panel B, we have more oxygen than NO. So the NO concentration is less than the oxygen concentration. And in the third panel, we have more NO than oxygen. Oops, that's not NO. That's NO too. Great. So we could do this without writing the rate law, but it'll just help if we write the rate law. The rate is equal to the rate constant times the concentration of oxygen to what power? The reaction is first order with respect to oxygen, so that's a 1. And what's the order for nitrogen monoxide? 2. So
The alligator always eats the bigger number, right?
the alligator eats the bigger number, yep. So this one's bigger, and that one's bigger. So if we're multiplying these, if the concentration of NO is larger, that's going to have a bigger effect, right, than if the concentration of oxygen is higher. So which one of these should be the fastest? C? Now I like math, I think in numbers, and so, conceptual question like this, I always end up translating it into math in my head to do it. So what if you really just want to do the math for this? What can you do? Well, you can say, let's pretend that, 3 of these is 3 molar. And so here we've got 3 for the oxygen and 3 squared for the nitrogen. Here we have, not 3, 1, 2, 3, 4. 4 for the oxygen and 2 for the nitrogen. And here we have 2 for the oxygen and 4 for the nitrogen. So this comes out to 32. This comes out to 16. And this comes out to 27. I may have done that wrong, but did you get the idea? Any questions?